Okay, so we've been talking about solving nonlinear inequalities. So we're going to do one more of those, and then we'll move to a new topic. So here's an example. So for example, please find the natural domain of how about this? 3x plus 4 divided by the square root of x cubed minus 10 x squared plus 25 x. Okay, so find the natural domain of that. All right. So, you know what that means. Find the natural domain of that expression. That means find all of the x's that you can plug in, and the result is defined. So find all x such that that expression is defined. You know, and to be clear, and this is just discussion, this is not really the answer to the question yet, is that you know, we could plug in 10, for example. You know, we could just ask like one point at a time, is 10 in there? All right. Well, if you plug in 10, we could just try to plug it in and see if it works. You'd get what? 3 times 10 and then plus 4 in the numerator. And then in the denominator, you'd get square root of 1,000 minus 1,000 and then plus 250. You know, so having a look at that, 1,000, not 100. So then, you know, I don't know what, you know, it doesn't turn out that the square root is like an integer or anything like that. But, you know, notice that we're not dividing by 0. The input to the radical is 250. I don't know the integer answer to that. There isn't one. But still, this works. You know, so, okay, that works. But as a different example, we could try to, say, plug in -1. Let's try that. Well, if we do that, the numerator would be 3 multiplied by -1, add 4, and then down here in the square root, well, -1 cubed, that'd be -1. And then -1 squared, that's +1, and then so that would be minus 10. And then 25 times -1, and then minus 25. So notice that you know, that'd be a negative being put into the square root. So that's not defined. So this is defined. This is not defined. Not defined in the end, because, you know, that's putting a negative into the square root. All right. So what we need to consider, what we need to figure out is what are the conditions? What are all the x's that make this defined? Well, there's sort of two major parts. There's the numerator. So, the numerator is defined everywhere. So considering the numerator by itself, what x's can you plug in to 3x plus 4? Any x, right? Nothing's going to go wrong. You could plug in positive x's, negative x's. Nothing's going to go wrong. And then if you consider the thing that's being put inside of the square root just by itself, just that, then you can plug anything at all into that, just considering it in isolation. Because you just need to cube something and then square something and multiply it by 10 and then multiply it by 25. That's all fine. But the fact that it's in a square root means that we need all of this. We need to avoid whenever that cube stuff is negative. Similarly, the fact that it's in a denominator means we need to avoid when it's 0 also. So here's what we need. So for the square root, to be defined, we need x cubed minus 10x squared plus 25x to be greater than or equal to 0. That's just saying you can't put negative stuff in there. But because it's in the denominator, so because the square root is in the denominator, in fact, for example, just concerning just that by itself, ignoring the fact that it's in the square root, ignoring the fact it's in a denominator, notice that you could plug 0 into this, right? If you were to plug in x is 0, then you'd get 0. All right. And if it were just a question of this being in a square root, that'd be fine, because what's the square root of 0? 0. But we can't plug 0 into this, because then you'd have a 0 in the denominator. So the fact that the square root is in the denominator means that it's not this inequality, but what inequality do we need to be true? So what do we need? Greater than. Instead of greater than or equal, we need just greater than, because when x cubed minus 10x squared plus 25x is equal to 0, when that's the case, that's a division by 0. All right. So after this consideration, the statement of the question is, find the natural domain of that expression. That's the question. And then after these considerations, we've come to the conclusion that what we must do is we need to solve this inequality. So to find the natural domain, of 3x plus 4 over square root x cubed minus 10 x squared plus 25 x, we will solve x cubed minus 10 x squared plus 25 x greater than 0. All right. So now we know what we need to do. So this is a nonlinear inequality. And all that means is that, if it were just this, just that, 25x greater than 0, and there's no x squared and no x cubed, that would be linear, and those are like the easy mode kind. You just, you'd have to divide by 25 or whatever. But the fact that there's x squared and x cubed and what have you, that means nonlinear. So this is a nonlinear inequality. And we have, so there's two kinds of nonlinear inequalities that we know how to solve in our class. There's the kind that has absolute value and every other kind. So this is not the absolute value kind. So this is a nonlinear inequality that's not the absolute value kind, and so we're going to use a sign chart. All right. So remember, the sign chart method proceeds in steps. So the first step is that we need to find the natural domain of that inequality. X cubed minus 10 x squared plus 25 x greater than 0. All right. So now it's at this point where historically students can get a little bit confused about what's happening. So let's be clear as we can about the question. So the statement of the question is, find the natural domain of that expression. So that's what landed on our desk. That's what we've got to do. Then after some considerations, we said, well, that means we need to solve that inequality. All right. And because it's a nonlinear inequality, we'll use a sign chart. And the first step of a sign chart is to find the natural domain of that inequality. So to find the natural domain of this expression, first we find the natural domain of this inequality. So can you see there's potential for confusion because we've got this very similar looking thing written down in two places. To find the natural domain of this expression, that means we have to solve this inequality. So the first order of business is to find the natural domain of this inequality. So remember, to solve an inequality, what that means is find all of the x's where it's true. Because, if you plug in some x's, it'll be true, and if you plug in other x's, it'll be false. To find the natural domain of an inequality is to find all of the x's where it's defined at all, false or true. So where is this defined? So the question is where, for what x? I'll say it like that. So where / for what x? Is the inequality defined? Well, again, in our class, right now there's basically just two ways where something might not be defined. When you, if there's a division by 0, or if there's a negative input to an even radical. So how many divisions by variables do we have in here? None. So we don't need to worry about that. How many radicals do we have in here? None. So we don't need to worry about that. Is there any x that you could plug into here where it would where it's just impossible to do it? Like, could you plug in? Well, if you plug in 0, let's think. If you plug in 0 just to that, then you'd get 0 minus 0 plus 0. So you'd get 0. So we're in agreement that you could plug in 0. Now, then you might ask, Well, if you plug in 0, the inequality would read 0 greater than 0, which is false. But that's not the question I'm asking. I'm not asking where is the inequality true. I'm asking where is it defined, false or true. So it's defined everywhere. Okay. It's defined for all x. So now the next step in the sign chart method, step 2, is called the 0 and factor step, which is to say that we want to take the inequality we're working on, so x cubed minus 10x squared plus 25x greater than 0, and we're going to do two things to it. We want to make one of the sides 0, and then we want to factor the non-zero side. So one of those steps is easy. This one, right? One of the sides is already 0. Okay, so check that off. And we want to factor this. Okay, so we'll do that. Now, most of our experience is factoring quadratics. You know, either the kind that are sort of the easy kind, where they're monic and the numbers product some thingy you can do in your head, or even if they're not easy with the quadratic formula. But this isn't even a quadratic; it's a cubic. So what do we do? Factor out an x. So should I divide both sides by x? No, I don't want to do that. Because, you know, if we were to divide both sides by x, so let me write down. So if we factor out an x, then it reads like this. And then from here you might say, okay, now I'm going to divide both sides by x, because that'll make my life easier. But you do not want to do that. Because the whole purpose of the sign chart method is so that you never multiply or divide both sides of the inequality by something. That's where things break. So you don't want to do that. All right. So even though it wasn't a quadratic to begin with, look, oh, there was a quadratic there after all. So does this? How does this quadratic factor? Very good. So x multiplied by one of the factors is x minus 5, and the other one is x minus 5. So you could write this maybe in the simplest way like this. X multiplied by x minus 5 squared greater than 0. All right. So what's the third step in the sign chart method? Solve something. Solve what? So specifically, so the sign chart method lets you solve an inequality. And then we did some work on the inequality to get it to here, and we made sure that all of our steps were safe. So these are all safe steps. And so on the way to solving this inequality, we're going to solve an equation. Because it turns out that solving equations is actually usually easier than solving an inequality. So we're going to take that inequality, and we're going to convert it to an equation. So notice that I wrote equal. And so now the structure of this equation, it's because we factored it up here, it's like, you know, super easy now. We've got this thing multiplied by that thing has to be 0. So one of those things is 0. So one possibility is that x is 0 because of that factor. And what's the other possibility? or x is 5. All right. So, you know, this step, doing the work, this careful work up here, makes this step usually pretty straightforward. Now, step 4, this method is named after this step, so this is where we make a sign chart. And so specifically, we will plot the natural domain from step 1 and the solutions from step 3. Okay, so the natural domain was everything, so, you know, fine. And then we found 2 solutions, so here's these 2 solutions. And now, to sort of visually separate stuff, I'm going to put some fence posts here. So 0 and 5. And generally speaking, like if you look at the example we did on Monday, the natural domain of the inequality was not all x. I think if memory serves, it was something like -8, because we had like a division by x plus 8 or something like that. And so -8 wasn't allowed. So in that case, you know, we plotted this, but we left a hole somewhere, and then the solutions I plotted with filled in. So you know, basically the things that get plotted here, the fence posts, are things from 1 and 3. And you could tell me any number of holes that you want and any number of solutions that you want. You could say, hey, let's make an example where there's 13 breaks in the natural domain and 14 solutions, and then we could plot them all. And you could say, and I want them to be here, 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 and here, and then, you know, it would be completely unreasonable to do a question with that much in it, but entirely possible. So now that we've done that, in each region we'll select a point. So something to the left of 0, how about -1, and between 0 and 5, how about 4, and beyond 5, how about 6. So those are in there. And so now we're going to evaluate the non-zero side from step 2 for sign. Specifically, what I mean is, you know, step 2, we ended with this inequality, x multiplied by x minus 5 squared greater than 0. So we're gonna plug stuff in to that side. So in each one of those regions. So there's going to be a pattern that in each region that looks like this. So we've got, you know, slot multiplied by slot squared, slot multiplied by slot squared, slot multiplied by slot squared. So just copying down that structure there. And now we're going to plug in the test points. So if we plug in -1 into this, then this first factor would be negative. And -1 minus 5, that's negative, so negative, like that. Okay, how about in the middle region? What's the pattern that we get? If we plug in 4. So that would be, this one would be positive, right? And how about this one? Negative. Okay, and then if we plug in 6, positive and positive, right? So this is this part right here, this is the sign pattern. And now down here we're going to write the overall sign. So if the pattern looks like this, negative multiplied by negative squared, then what's the overall sign? Negative. You know, because the negative squares away, it gets squashed, and then we've got one more negative, so negative is what results. And then what's the overall pattern here? Positive. And in the rightmost region? Positive. All right. So notice that this is different than the example we did on Monday in a couple ways. So for example, on Monday, the pattern was alternating. It was something like negative, positive, negative. Or maybe it was positive, negative, positive. I don't remember. But when students are doing this, very often they reach the wrong conclusion that it always has to be alternating. But here's an example where it's not alternating. It's negative, positive, and then positive again. And you could give me any sequence of the words negative and positive, and I could make an example that does that. So we could do one that's, you know, 4 negatives in a row, then alternating negative and positive as long as you want, and then a bunch of positives, whatever you want. We could make one like that. All right. So now that we have the sign chart, we're able to make a conclusion. And the way these work is that we cut the natural domain into parts, and now there's 3 parts, and we're going to want all of the same kind. We either want all the parts labeled negative, or we want all the parts labeled positive, and whichever one you want depends on the exercise. It can be different on different exercises. Maybe on one exercise you want the negative parts, and on the other the positive parts. What do we want on this one? The positive parts. So we want the positive regions on this one. And why is it that we want the positive ones?
Because our inequalities are greater than.
Exactly this. Because remember, in the end, what a sign chart is doing is it's solving an inequality. That's what it's doing. So all of the questions in the end refer back to the inequality. The inequality says blah blah greater than 0. So we want the positive regions. All right, and you can see that there are 2 positive regions. Okay. So I'm going to draw that. So we've got 0 and 5, and we're saying we definitely want the stuff between 0 and 5, and we definitely want the stuff beyond 5. But we also need to ask the question, what about the boundary points? So on Monday, the answer to the question is what we wanted one of the boundary points but not the other. And you know, for you can make any arrangement, and I can make a question where, and you say I want it to be so that make a question so that we're going to keep that one but not that one, or the other way around. I can make a question that does that. So what's going to be the case here? Do we want 0? No? Why not? In the end, it comes down to the inequality. So, the question of do we want 0? Well, you plug it into the inequality there, and you would get 0 multiplied by negative 5 squared greater than 0. So that's the inequality that results, and of course that simplifies to 0 greater than 0, which is false. So we don't want 0. Okay, do we want 5? Yes? So let's see. The way to check is that you plug in 5. Do we want it? So plugging it in there, we would get 5 multiplied by, and if you plug in 5 there, you get 0 squared greater than 0, and that inequality reads 0 greater than 0, and that is false. So do we want 5? We don't want 5. Now, how could we make it, ignoring this, if the question if the question started right here, if none of that stuff was there, the question just started right here, how could we make it to where we actually would want 0 and 5? Yeah, we change that to greater or equal. And then, we'd have greater or equal all the way down, blah, 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 to right there. And then that would say 0 greater or equal 0. And then we would want those points, right? Okay. So, that's the answer. And then usually the question says, give your answer in interval notation. So how do you write it down? Well, 0 to 5, that's one part. And then union 5 to infinity. Any question about this this exercise? So what it's saying, in the end, the question was, what x's can the statement was, find the natural domain of this expression. And the answer to the question is, these are the x's that you're allowed to plug in. So you can plug in stuff between 0 and 5, but not 0 and not 5. Those won't work. And you can plug in stuff more than 5. And you can see that's in agreement with our just little exploration here. We said, can you plug in 10? And we said, and we determined, yeah, you can. And you can see that 10's in there. And then we asked, can you plug in -1? And the answer was, nah, you can't plug in -1, and you can see -1's not in there. Any question about this this idea? So now, a couple things to sort of recap is that this is probably the most complicated thing that we're going to do this semester. It's got lots of steps. The reason why it has lots of steps in the end is because it's a delicate process. You want to make sure that you don't make any errors. And it's this process which is being graded, not just you writing that down at the end. Okay, it's the process. So I want to see, making the sign chart, and I want you to say, in this case, we want the negative regions because the inequality says whatever. And we do want this boundary point, and we do not want that boundary point. So to make your, answers clear. So, that's what's being graded, sort of this rigorous process. Now, many of you are going to end up taking calculus very soon. Calculus, the one that comes immediately after this, 1325. And it is not an exaggeration to say that about half or 3/4 of all of that course is doing this. The way it works, though, is that the statement of the question, it won't say find the natural domain of this. Rather, it'll say find the local minima of this, or find the local maxima of this. Find where the output is biggest, or find where the output is smallest. Or it'll say, find where this is increasing and where this is decreasing. So what you do is you take this, whatever this is, and you do a little bit of work on it, some calculus work that we don't talk about in this class. There's a math operation called computing a derivative. So you take this, and then you calculate a derivative, and then immediately after you've calculated a derivative, you make a sign chart of the derivative. And so calculating the derivative takes about that much work. And then finding the sign chart of the derivative is the rest of the work. So, this is like a very important technique for this part of math. Any question about it? Okay. Next. So, definition about a new thing. So we've been talking about equations and inequalities and things like that, and now we're going to talk about a thing called a relation. So a relation is a map mapping from a set called the domain to a set called the codomain. So that's the definition, and in many ways that's a definition that only a mathematician could love. So let's have some examples of its use. So for example, so something like 1, 2, 3. This will be the domain, and then maybe over here is like 5 and a triangle, and this is the codomain. So one set called the domain, another set called the codomain, and then the mapping I will indicate with arrows. So like this. So maybe 1 maps to 5. So what you'd say is that 1 is related to 5. Okay, and maybe 1 is also related to triangle. So 1's related to both of them. And then maybe 2 is related to 5. And maybe only 5. And 3 is related to triangle. So such a thing is called a relation. So this is not really what we're going to talk about, so I'll just briefly say what this is. You can ask basically two kinds of questions. You can say, what is 1 related to? And the answer is it's related to 5 and triangle. You can also ask the question sort of in reverse. You can say, what's related to 5? 1 and 2. Because 1, there's a path from 1 to 5, and there's also a path from 2 to 5. All right. So, we use the word relation in everyday usage, right? Like the word relationship, meaning like a romantic relationship, for example. So in that case, the two sets, the domain and the codomain, would be the same set. So it's the set of all people. And then you could say, well, this one's related to that one. Or instead of maybe not, if you don't want to do romantic relationships, then you could just do familial relationships. This one's related to that one. Okay. Another example that's in everyday life is something like Facebook. So in this case, again, the domain and the codomain are the same. It's the set of all people who have a Facebook account. And Facebook's keeping track of, this one's related to that one, because they're friends or whatever. Or, when you log into Facebook and you look at, that person's stuff, they're keeping track of all this information. So that information, the mathematical name for it is a relation. All right, fine. But we are interested in a specific kind of relation, not just any kind, but we're related in a. We are interested in a kind of relation called a function. So a function is a relation where every element of the domain maps to one element of the codomain. So now, this, what I drew up here, is not a function. It's not a function because notice that 1 relates to two things. Right? So it's related to 5 and triangle, and that's not allowed. So you can sort of think of this like a machine, and this is like the input side, and this is the output side. And you can sort of see it like this, like if you put a 3 in as input, then a triangle will come out. And if you put a 2 in, then a 5 will come out. But if you put a 1 in, 2 different things come out, a 5 and a triangle. So that's not what we're talking about. That's a relation. A function is where you put an input in and only one output is permitted. Sort of like the vending machine, right? You press the button and one thing comes out, not 2 things. Okay, an example would be, we could take that same relation and we could sort of trim it down to how about this? Maybe 1 is only related to triangle now. Two is related to 5. And 3 is still related to triangle. So notice that the way this works, now there's 1 arrow leaving every element in the domain. Oh, I turned it off. Darn. Every once in a while I rest my hand on that button. Just reboot it here. You can do it, machine. All right. So notice that 1 arrow is leaving all of these. So 1 arrow leaves. Every element of the domain. So this is a relation, and this is also a relation, but it's also a function, because every function is a relation, but not the other way around. So not a function, yes, a function. All right. So it's typical to name this process, to give it a name, because we're going to end up using it a lot, with computation. So I'll name this whole thing, I'll name it f. That's a very common name for function, probably because the word function starts with f. And we could use it like this. So for example, I could say, please evaluate f of 1. So what's f of 1? Meaning that if you put a 1 in, what comes out? Triangle. So maybe that's one question, and then maybe question number 2. I think it's really obvious, but still, all right. I'll say, what about evaluate f of 2? What do you get? 5, right? You put 2 in, and then 5 comes out. Another. Well, I could also ask this. This is going to be important too. How about what's f evaluated at 8? This is undefined. It's undefined in the end because the domain contains those elements, and 8's not in there. Okay, that's just like if we walked up to the vending machine, and I could say, well, what happens if you press the button E4? And assuming there really is an E4 there, then we could figure it out. What happens? But then I could say, what happens if we press the button giraffe? And then well, There's not a button named giraffe. It's not in there. Okay. Here's a different question that we can ask about the same thing. We can say solve now. So solve. So how about let's solve f of x is equal to 5. Now the question is sort of like you're standing over here. If you can imagine that this is a big building and you're over here and you witness a 5 come out. The question is what must have been the input? 2. Okay. And I could ask, well, how about let's solve this one. F of x is equal to triangle. If you witness a triangle come out, what must have been the input? 1 or 3. Or a giraffe. And then I could ask, well, how about please solve, say, f of x is equal to square. What input can you provide so that a square will be output? None. So in this case, there's no solution. And that's just like walking up to the vending machine, and this one might be like, well, how do I find a Reese's? Well, you press button number 2. And how do I find a Snickers? Oh, that's common. So in fact, you can either press that button or that button. And then this one could be like, how do I get a fettuccine? And then, you know, there isn't a button for that on the vending machine. All right. Fine. So examples. The most common kind of function that we will deal with in our class are actually not those arrow thingies, but the most common kind are going to be functions defined by expressions. So I could say, for example, let f of x be the square root of x, and let g of x be some other function like 13x plus 14. And then we could have a sequence of questions. So how about, you know, g evaluated at 10? So what that means is that what this is saying is that this is what g does when you put an x in. It does that. And now I'm asking, well, what does it do when you put a 10 in there? And what it does is you've got a slot here, so 13 times slot, and then plus 14. And you're just supposed to replace whatever goes in there. So something like, you know, oops. So 13 multiplied by 10 plus 14. So that'd be 144. All right. So you need to be a little bit careful when you do it, because if we write g of, say, w plus 4 like this, then here is an error. So 13 multiplied by, so I'm supposed to replace the x with w plus 4, so 13 w plus 4 and then plus 14. So that's an error. What's wrong with this? Well, it's that it's all of this, right? So without those parentheses I just put in there, the 13 wasn't multiplying the 4, but now it is. So generally, when you're plugging things into other things, you need to write a slot, a set of parentheses. Okay. 2 more things, and then we can be done for today. So how about f evaluated at 16? Well, that'd be square root of 16. And what's the square root of 16? It's 4. Now, at the beginning of the semester, long back in prehistory, you know, we said that the square root of 16 is 4, and it is not plus or minus 4. Now, I agree entirely that when you square negative 4, you get 16, and when you square positive 4, you get 16. No dispute. but 4 is the square root of 16. Why is it not plus or minus 4? Well, according to the definition, but that we said at the time. But what I'm saying is, as of today, we have another way to say it. Is that if this was plus or minus 4, then how many outputs would this have? 2. But we want the square root to be a function, and so it can only have one output, and that's the one that we choose. Finally, and this is the last thing, is we could do the following. We could say, you know, what if we do like a f of g of x, like that? Okay. So that would mean that you know, doing it sort of one step at a time, like peeling it like an onion. So f does that. So, and then a g goes in here like that. And then now I can replace g with what it does. So g does this. So what's happening here is that this process is called a composition. And what's happening is that it sort of works like the following: is that we have an x, and then first it's going to visit the machine, the g machine. So we do g to it, and then out comes 13x plus 14. So that's the output of the g machine. And now we're going to use the output of the g machine as the input to the f machine. So we're going to do f to that. And now we have this. So that's what this is. Now, if we were to reverse the order of those machines, the result will be different. So if we were to do x first to the f machine, then we would have square root x, and then give that as the input to the g machine. Then we'd have 13 multiplied by square root of x plus 14. So those are different. Putting these functions, these little machines in this order, this is called composition. And this is the reason why we're looking at functions. This right here is the whole thing. The reason is because if we can break down this whole complicated thing into little bitty parts that we understand, like that part is easy enough to understand, and just that part is easy enough to understand, then we can say that, oh, and when you assemble them like this, then we can understand the whole thing. So in human history, this has been very important, but notably, Ford Motor Company, of course, makes cars. But historically speaking, what are they most famous for? The assembly line. And that's all that this is we're saying that you take an input, and first we're going to do that, and the output of this is the input to the next thing, all the way down the line. And if you understand every single step along the way, because there doesn't need to be 2, there could be 22. If you understand every step along the way, then you understand the whole thing. All right, so that's all that we have for today. I hope you have a wonderful Wednesday.